Hi guys, you're welcome to my channel, and today wants to look at optics practical. But before we look into the practical, I'd like to discuss everything that you need to know as far as optics is concerned in order for you to be able to guide your experiment. When you are doing physics experiment, one thing is to be sure of what you are doing. That's number one. Like, you want to be very sure that what you are doing is correct. Number two is that you want to actually be correct. Like, at first instance, you want to be sure that what you are doing is correct. And the second instance is that you actually want to be correct. So in order to do that, there is always need for you to put in place. What are you to put in place? Number one is to understand the theoretical background of that experiment. Like, for example, now we want to do experiments that has to do with triangular prism and also a plane mirror. You need to first of all understand what is the theoretical background of these two things. When you understand the theoretical background, then you can carry on with the experiment. Because when you want to do experiment, what you want to verify is a theory. Am I right? What you want to verify in any experiment is a theory. So you cannot verify a theory that you don't understand. And that's why I quickly want to point out everything that you need to know about any experiment that has to do with what? Prism or glass. Of course, you will agree with me that when you talk about prism and glass, you are talking about light wave. And when you say light wave, I like to divide the board. When you say light wave, you are simply referring to an electromagnetic wave. Light wave is an electromagnetic wave. That is a wave that requires no material medium. There is no need for any material medium for its propagation. That's what we refer to as electromagnetic. So, when it comes to light wave, and you talk about what? Prism and plane glass, then we want to look at the properties of light. So when you now talk about the properties of light we want to look into, we have a lot. We have one, reflection. That's properties of wave. All wave can be reflected, either mechanical or electromagnetic, either transverse or longitudinal. Are you getting it now? So they can all be reflected. And we also have what? Refraction. All wave can also be what? Refract, either longitudinal or transverse. Then diffraction. All wave can diffract, either longitudinal or transverse. Then we have polarization. All wave cannot be polarized. Are we together now? Only transverse wave can be polarized. Am I making sense now? So since light wave is an example of what? Transverse wave, definitely all these four properties is what light can exhibit. Are you getting it now? But whenever you now have experiments, I want you to get this very right now. Because if you get this very right, you don't need to panic when you are carrying out your experiment. You'll be definitely certain of what you are doing once you understand all these things I'm about to explain. So if a teacher is doing rubbish, you will know. If you are doing rubbish, you will know. Are you getting where I'm coming from now? So you can easily cross-check your answer at every point in time. So as a student, you might be assisted. So when they bring a reading from you from somewhere, that reading, are you sure that is correct? It is only when you understand the theoretical background of that particular experiment that you can be sure that what you've done, you are right or wrong. Because examiner will never and never go back to the lab to go and carry out the experiment before they can mark your work, mark your scripts. All they are checking out for is what you're supposed to know by yourself. Because theoretically, if this one increase, this one's supposed to decrease. If this one decrease, this one's supposed to decrease. Those are the things that theory talks about. So if theory talks about it, then you carry out experiment. Experiment must also fulfill that. Do you understand that now? So as a student, because when teacher teach in class, we really don't understand. That is what happens most times. And even teachers that come to class to teach, most times they come after reading the textbook and come and what give you the same thing. Because most physics teachers, I'm very sorry to say this, most physics teachers, all they are all about is just to be one chapter ahead of the students. Are you getting it now? Not that we really understand that particular what concept. And understanding that concept is what can build confidence for you as a student. Is that taken now? So if that should be the case, whenever you now have experiments that has to do with plane mirror, are you seeing this now? Plane mirror, pins. Are you seeing this now? Prism. Either triangular or what? Rectangular. Either of it. Whenever you have experiments that has to do with all these apparatus here, no doubt, you can only use them to verify two of all these properties. Am I making sense now? You can either use this to what? To talk about reflection or to talk about refraction. Am I making sense now? So, if you want to talk about diffraction, there might be need for other things. Are you getting it now? Such as an open slit and so on. If I'm to talk about polarization, there might be need for me to introduce what we call lenses. Are you getting it now? And in a critical case, maybe a curved lens, a curved mirror rather. Are you getting it now? As the case might be. But if you look at what we have here, we have nothing to do with those things that we can use to verify these two. For that reason, for this experiment, there is need for you to understand reflection and refraction. Am I making sense now? So I'm going to break the concept of reflection down so that you understand it, the theoretical background mathematically. Are you getting it now? And also refraction and every other thing that can come in line with them. So when you understand these two very well, if you are carrying out your experiment, you know what to watch out for. You know when you are right, you know when you are wrong. If it tends to manipulate the reading, maybe you find it difficult to go ahead with the experiment because of time or something, manipulating your reading, you'll be sure that you are going to have an accurate result. Am I making sense now? So let's look into that. So we are starting with the very first one, which is reflection. When you say reflection, literally, what are we talking about? We are talking about a wave that changes its direction as a result of an obstacle. That is, you are moving now, this is very open place. By the time you move and then you see something that blocks your way, let's take for instance that I have this stool here now, and the stool is here, and I'm walking straight right now, and this is an obstacle to me now. Am I making sense now? So I have to change what? Is that I take it away from that place, or I change my direction to pass the side. Are you getting it now? So when it happens to a wave like that, when wave encountered an obstacle and it changes its direction, that ray of light that takes another direction is called a reflected ray. Am I making sense now? So let's take for instance that you have a plane mirror here. So whenever you see something like this with this dash dash, it represents what? A mirror. In any diagram that you see and you see this, know that they are talking about what? A mirror. Now there is now what? A ray of light that is traveling like this. You know, light travels on a straight line, isn't it? Okay, and the part in which light travel is what we refer to as ray. So when this thing travels straight like this, you know, the ray is not human, isn't it? It's not possible for the ray to come and pick off the what's it called, the plane mirror away from this place. So there's nothing that will happen than the ray to do what? To change its direction. Are you getting this now? So when it changes direction, we have this. Are you getting this now? So if you look at this now, this is an incident ray, right? And this is what? A reflected what? Ray. There is an imaginary line between these two. Are you seeing it now? That imaginary line is perpendicular to this surface. That imaginary line is what they always called normal. It's what they call what? Normal. It's what they call what? Normal. They call it normal. So this angle here, this ray of light that you are seeing, are you getting it now? Is referred to as the angle of incidence. So let me call it θ1. And this one, the angle between this one and this one, let me call it θ2, and that is what we call angle of reflection. Am I making sense? Are you getting this now? Now, there are now two laws that can help you here. Are you getting this now? How many laws? Two laws. What the law states is that the first one, it says the incident ray, the normal, and the reflected ray, they all lie on the same what? Plane at the point of incidence. So this is the point of incidence, and when you look at what? The incident ray, the normal, and the reflected ray, they are all on the same line. Am I making sense now? So the second one is that what? The second one is that the angle of incidence is equal to angle of reflection. So that means that θ1 will equal to θ2. So this glass that you have vertically like this, it can as well come horizontally. Am I making sense now? So if I have it horizontally like this, and this is what? An incident ray. You must be familiar with this very well. I say it now. And this one is going to be what? A reflected ray. And this is what? An imaginary line called normal. I say it now. The same principle holds. This one is going to be our θ1, and this one will be what? θ2. And θ1 will equal to θ2. Am I making sense now? So this is incident, this is what? Reflected. Now, when we are carrying out experiments, it's very important for you to note something, because examiner is not there. You are not going to be there to tell the examiner that this is what I've done, but you must present your results in a way that the examiner did not need your assistance to understand. What do I mean? Look up. If I have a diagram like this, it's still the same diagram. Look at this diagram here. And this is an incident ray. No, I don't even know. So let me just have it like this. And here is normal. So now label this θ1 and label this θ2. How do you want me to know the one that is incident and the one that is what? Reflected. So who can tell us? Let me label it. This is O, A, N, and B. So you can tell which one is reflected ray, which one is incident ray. Somebody? Okay, so somebody say right now we can't tell the one that is incident and the one that is what? Reflected, until we added what? Arrow. Are you getting it now? So it is very important you understand why we are putting these marks. So you must not forget it, because it is this mark, this arrow that you are seeing, that will let us know the one that is incident and the one that is what? Reflected. So if I put this arrow here and I have this like this, you know, since morning I've been saying that this one is what? The incident way. Abi? But now, looking at this arrow now, this one is what? The incident. So the arrow tells you the direction of the light. I hope it's clear. You get that now. So when you get your plain paper and you carry your experiment on this plain paper, don't forget, it's very important, don't do what? Don't forget to always indicate your arrow to show the direction of light. Very important. Now, this is very easy now. Now, the question can become something so complex that examiner will tell you that if a ray is incidented or a ray of light is inclined at a certain angle on a contour or on a curved mirror. So, okay, I don't want to use on a corner, let me use that now. On a corner reflector. I think that statement is better to be used. A corner reflector. What am I corner reflector? A corner reflector is a mirror that is inclined at probably 90 degrees. This is a mirror, this is a mirror. If I now do what? If I incline them at 90 degrees, they become corner reflector. Are you getting it now? And whenever you have a corner reflector, listen, whenever you have what? A corner reflector, there exists two rays. One ray is called the inbound ray, and the other one is called the exit ray. Are you getting it now? The inbound and what? The exit. Now, what always arises here, whenever you are having what? Inbound ray and exit ray, what will happen is that examiner will want you to look for the angle between the inbound ray and the what? Exit ray. How do you go about that? So let's look up. I think I can clean this now. So let me say I have a corner reflector like this. This is a corner reflector, a mirror, and another mirror. Are you seeing this now? Then I have what? A ray of light that is inclined at an angle of 60 degrees. Are you seeing this now? Can you see the way it comes now? It's inclined at an angle of what? 60 degrees. That is, it strikes this what? This surface at angle of 60 degrees. So if this is what happened, right here, you know, this is going to be the normal. Abi? So we actually don't know the angle of incident yet. Am I right? Remember the question. We are asked to look for the angle between what? The inbound ray. Inbound ray is the ray that what? That strike, which is this one. Are you getting it now? Exit ray is the ray that go out that there's nothing to reflect it again. Am I making sense now? That is ray that find its way out of the boundary. You know, this one is still in the boundary. When this one strike here, it's going to what? Strike again. So that ray that is able to make his own way out of all this obedience. Right? Getting it now. That's how we refer to as what? Exit ray. So if the question says find the angle between what? The inbound ray and the exit ray. How do we go about it? So pay attention now. This one strike, isn't it, at angle of 60 degrees according to the question. So we have a normal from that point, isn't it? By default, there will be an angle of what? There will be a ray that reflects, isn't it? So this one will come to this side, like this. Abi? Isn't it? And when this one strike this place, what will happen again? This one will change its direction like this. Abi? So this one has this. Am I making sense? So which of these is what? Exit ray out of the three rays? The last one, right? Correct. So we are now looking for the angle between this and this. Now, do you know the crazy things here? If I keep on drawing this line like this, and I draw this one like this, they meet at a particular point. Are you getting it now? But I don't want to go through that stress now. What I'm telling you is that there might be some questions that they will give you a diagram that intersects like that and ask you to find the angle there. They are still asking you the same question. Are you getting it now? We might consider that as we move on. So how do we find the angle between them? Very easy, right? You know, from here to this place is what how many? From here to this place, 90, right? So if here is 30 degree, if here is 60 degree, here will be what? So the angle of incident is going to be what? 30 degree. And this place is the angle of what? Reflection. Abi? So if here is 30 degree, here will be what? 30 degree. Why is it going to be 30 degree? Theta 1 is equals to theta 2, correct? So this place is also what? 30 degree. Am I making sense now? Okay, so if here is 30 degree now, remember this one also is going to have what? A perpendicular, normal. Are you getting this now? Thank you. A normal is always perpendicular. Am I right? Now, what will happen right now? If there is 60 degree, sorry, I said 60 degree. If there is 30 degree now, are you getting this now? We have an angle here, and we have another what? Angle here. Abi? So let me say this one is theta 1. This one is theta 2. This one will be what? Theta 3, and this one will be what? Theta 4. Abi? So we've gotten theta 1, theta 2. We are looking for what? Theta 3 and theta 4. So how do we go about it, guys? How do we get this place? Alternate angle. Does everybody say that? Okay, you say alternate angle. How do you know they are alternates? Okay, if there is 30 here, will be what? 60, right? Okay, so you say here and here alternate. How do you know they are alternates? Because they form what? Z. Okay, like this, like this. Okay, like this, like this, like this. Isn't it? Okay, I think that's primarily fine. I get to this now. So to layman, you correct absolutely. But you know, when the line forms Z like this, you can extend this leg like this. I see it now, and extend this like this. This line and this line, what are they? They are what? Parallel. So because this line and this line are parallel, this angle will be alternate to this angle. Do you understand that now? Therefore, here is what? 60 degree. Am I making sense now? So if here is 60 degree, here will be what? 60 degree. Do you understand that now? So how do we now get the angle between them? So for us to get the angle between them, it's quite easy. All we just need to do is to calculate this angle. 30 plus 30 plus 60 plus 60 180. So the angle between the exit ray, the inbound ray, and the exit is what? Is 180 degree. So because these lines are parallel, you can as well say it is 0 degree. You don't want to be mathematical. Are you getting this now? Because they are parallel, you can as well say what? It is what? 0 degree. But 180 degree is fine, since that is what you calculate. Do it make sense like that? Okay, so I think that example is quite simple. So let's look at the one that is kind of complex a bit under this corner reflector. Okay, can I clear this now? Okay, so I want to believe everybody understand this. You understand how it works now? So I'm very sure that you must have been seeing questions that look like this, probably for those of you that study extra, and you'll be like, how do we go about this? Okay, so I believe by now you know how to go about it. So we are still on that. So let's look at this one now. Let's say I have this. This is an imaginary line, and this is what? A mirror. I have a mirror like this, and then I now have another mirror like this, and the angle between this normally the first one will be the two mirrors are perpendicular, Abi? But right now the two mirrors are not perpendicular, they are slightly away by 10 degrees. Are you seeing it now? They are what? Slightly away by 10 degrees. Let me clean that so that it will be well written. Okay. They are slightly away by 10 degrees. So if they are slightly away by 10 degrees, So what's the question? The question now states that if a ray of light now strike just like it was before, a ray of light strike at 60 degrees. So the question now states that we should find what? We should find the angle between the inbound and the exit ray. So how do we go about that? Very simple. We go by, this is normal, Abi? Yes. Okay, so this one is going to what? Strike here, Abi? And this will be the exit ray. Am I right? Okay, so here is also what? Perpendicular, Abi? Normal, yeah, sorry, normal, anyone. So it's fine. So if this one is 60, this one will be what? 30. And this one will be what? 30. Okay. So what will be the value for this angle here? Let me make it better. Okay, so this is normal, this is perpendicular to this one, right? Okay. Is what? It's 60. Okay. So who else? I'm with you. Is what? 70? No. Look up. Look up. Look at something here. You know, this line is not perpendicular. Are you getting it now? But this one here, listen very well. This one here is perpendicular to this one. Abi? But why is looking slant like this? Because this is also what? Looking slant. Am I making sense? And that's why I quickly help you to redraw it. Now, look at something here. If I draw an horizontal line from here, can you see? From this straight line here, this is a very good perpendicular line because it comes straight, right? So you have an angle here to be theta. Am I right? Am I right? Okay. So for us now to get our actual value, am I making sense? We need to know the value of this theta. You know, from here to this place is what? Is 60, right? Like we said. And this 60 is supposed to be alternate to this, isn't it? So this 60 will be alternate to this complete angle here. Am I making sense now? Not to the angle of incidence. Are you getting what I'm showing there? Yeah? Not to the angle of what? Incident. It is from this line that we are going to have this to be 60. So that means the angle of incident, let's call it theta 3. Are you seeing it now? Plus this small angle here, nice, let me just call it theta s, must give us what? 60 degree. So for us now to get theta 3, and let me call this one theta 4. You know, theta 3 and theta 4 has to be the same thing, isn't it? Because angle of incident and angle of what? Reflection. Alright? I'll teach you some small math here now. Alright? Look at something. If this line here, this blue dotted line, if it is perpendicular to this line, are you seeing it now? And this line is perpendicular to this one here. Are you getting it? The angle between this line and this line is the same thing as the angle between this line and this line. You get the explanation right? Look again. This blue line here is perpendicular to this one here. Let me label. Let me call this one OA. Are you seeing it now? Let me call this one NB, and call this one let me call this one C, and call this one D. I just leave that anyhow so that you get what I'm saying. So if you look at line NB, I see it now. Line NB is perpendicular to line OA. I see it now. And line DC, I see it now. Line DC, let me call this one E. I see it now. Line OE rather is perpendicular to what? DC. So if that is the case, if MB is perpendicular to what? OA, and what? DC is perpendicular to what? OE. The angle between MB and then DC, are you getting it now? Must equal to the angle between what? OE and OA. So if the angle here is what? 10, then the angle here is also going to be what? 10. Therefore, this small theta is what? 10, and theta 3 plus 10 equal what? 60 degrees. So theta 3 is going to be what? 60 minus 10. And we are going to have what? 50 degrees. Are you getting it now? So this angle here is what? 50. And this angle here is also what? 50. Do you make sense like that? So we have this to be our exit ray. This is what? An incident ray. Carries here now. So the question now is, what is the angle between them? So let's read. 30 plus 30 60. Plus 50 plus 50 160. So 160, that means this angle here is going to be what? 20 degrees. Abi? Okay, so if I extend this line like this and I extend this line like this, are you seeing it now? The angle, this is what? The inbound, Abi? And this is what? Exit ray, right? So the angle between them is going to be what? 20 degrees. Do you get that right now? So that is how to find that, and I think this is kind of is more kind of tedious compared to what we have earlier. So I think by now we can move to what we call refraction. Now we all understand reflection right now, right? So that's how to go about reflection. So the next one you need to understand now is what we refer to as refraction. And what we call refraction? Refraction is the change in direction of a wave when it passes from one medium to another. Now, that definition is not actually correct, because at times when a wave moves from one medium to another, the direction might not change. Are you getting it now? But some other properties will change. So in a nutshell, refraction is when a wave moves from one medium to another. Whenever a wave moves from one medium to another, some of its characteristics will does what? Change. So the characteristics that will change now depends on the angle in which the ray or the wave enters into another medium. Are we together? So you need to consider the angle in which it does. So let's look into that. So can I clean this now? Okay. So we look at refraction now. I hope everybody is getting the explanation right. Okay. So refraction now. So we can't come and kill ourselves with it. Alright? So let's see if it's going to blow here. Alright, it's fine, guys. So let's look up now. Refraction. Let's take for instance that I have two medium. Let me call this one air and call this one glass. Are we together, guys? Air and then glass. You see, the first thing that you need to know about every medium, the first thing that you need to know about what? Every medium is refractive index. Are you getting it now? When a medium, and what really determines the refractive index of mediums is the density of the medium. When a medium has a very high density, are you getting it now? Its refractive index tends to be what? High. When a medium has a low density, the refractive index of that medium is said to be what? Low. Are we together? So when you compare glass and air, of course, which one is more denser? Glass, Abi? So that means that refractive index of the glass is going to be higher than that of what? Air. So the refractive index of air is 1, the same thing as that of the vacuum. Am I making sense now? But when it comes to glass, the refractive index is within around 1.5 to 1.6. Are you getting it now? So let me say the refractive index is what? 1.6. Am I making sense now? Okay. Because of this property, when a wave travels from air to water, there will be change in something. Normally, these are things that are likely to change whenever a body refracts. One, the direction. Two, the speed. The direction can change, the speed can change, the wavelengths can change. You can see three things that are likely to change. And every other thing that you might want to talk about, but one thing will not change, no matter what. That's what? Thank you. The frequency. The frequency would not change. But every other things, they are likely to change. When I say likely to change, they might change, they might not change. But one thing is very certain that is going to change, and that is the speed. That one is very certain. What is under probability that it might change, it might not change, is what? Is the direction. Because for the direction to change, it depends on the angle in which the wave enters into another medium. Are you guys getting this now? Depends on the angle in which the wave enters into another medium. But you see the speed, it is a constant thing, it has to change. And what will never change, no matter what, is the frequency. Am I making sense now? So the wavelength will definitely change. The only thing that is under probability that it will change or not change is what? The direction. Do you get that clear now? So now let's say that a wave enters directly. That is, it enters like this, straight down. The angle is 90 degrees. So the direction will also be what? Straight down. Are you seeing it now? The wave enters straight, it will not change its direction. But what will change? Its speed will change. Am I making sense now? So velocity of light, the speed of light in air is given as, let's say VA, is given as what? 3 times 10 to the power of 8 meter per second. Am I making sense now? So the speed will change when it enters into the glass. Am I making sense, guys? Yeah. So what we want, the speed of light in the glass, we don't know. For us to know, we need to go back and revert to what we call Snell's law. Am I making sense now? Snell's what? Snell's law. So Snell's law can help us to know the speed of what? Of light in glass. Do you understand that now? So how do we get that? So take them. We can say the velocity of light in another medium is equal to what? The speed of light in air divided by the refractive index. What do I mean? Look up. Look up. When you're looking for what? The speed of light. When you're looking for what? When light travels from air into another medium, the velocity of light in that medium, the velocity of light in that medium is the speed of light in air divided by the refractive index of that particular medium. Do we get this clear? Okay, so now there's a problem here. Listen, there is what? A problem. What is the problem? If you have VA over N, look, let me just give you directly. If I have that velocity of what? Light in glass divided by the refractive index of what? Of the air. You know, light is coming from air to the glass. So we have what? Velocity of what? Of light in glass divided by the refractive index of air, which is the medium where the light is coming from, equal to the velocity of light in air divided by the refractive index of glass. So if I'm now looking for the what? the velocity of light in air, in glass rather, my result will now be what? Vg equal what? NA divided by what? Mg. Do you understand this now? But since the refractive index of air is what? 1. Are you seeing it now? Since the refractive index is what? 1, then the velocity of air is going to be what? The velocity of light in air is what? 3 times 10 raised to power 8 divided by the refractive index of glass 1.5. Sorry, 1.6. Okay. So 3 divided by 1.6, what do you have? 1. So we have 1.875 times 10 to the power of 8 meter per second. So that gives you what? That gives you the velocity of light in glass. You can see that the speed does what? Is it increasing or decreasing? It does what? It decreases. So you can see that the speed of light in air is 3 times 10 raised to power 8 meter per second, but in glass is what? 1.875 times 10 raised to power 8 meter per second. So if it is in water, for the refractive index of water is around 1.33. Are you getting it now? So if I want to look for the speed of light in water, let's say this is water now. Light move from air to what? Water. So the refractive index will become 1.33. Then I'll just go by this formula again by saying what? The velocity of light in water, that will be velocity of light in air divided by the refractive index of water. So the velocity of light in water will now be 3 times 10 raised to power 8 divided by what? 1.33. So 3 divided by 1.33, what do you have? Is that what? 2.256 times 10 raised to power 8 meter per second. That's to tell you that light can travel faster in water than it does in glass. Am I making sense now? And what does that tell you? That tells you that the higher the refractive index, the lower the speed of light. Am I making sense now? So you need to understand this should in case it rise up in the theoretical part of the experiment. Okay, so now let's see if the light entered in a particular angle other than 90 degrees, what will happen? Can I clear this? Please, is there anybody that is not getting the explanation clearly? Do we have anybody? Okay. So now let's say I have this now. So we are still dealing with N, whose refractive index is 1, and the glass, whose refractive index is 1.6. So let's say the ray of light travels and enter at an angle of incidence of theta 1. Sorry, the angle of incidence is supposed to be within the normal. Theta 1, and this is what? Incident ray. Now there's something you need to get clear here. Listen, before I can continue with the diagram. You know this is the normal, Abi? Please note this very well. Whenever light travels from a region with low refractive index, remember, a region with low refractive index is a region with low density. Are you getting this now? When light travels from a region with a low refractive index and enters into a region with high refractive index, it changes its direction towards the normal. Note, it's very important. It changes what? Its direction towards the normal. That is, this light is going to travel close to the normal. Can you see now? So this is what? Refracted ray, and this is angle of refraction, theta 2. Am I making sense now? But if the light is traveling from a medium that has high refractive index, going to a medium with what? Low refractive index is going to refract away from the normal. You need to note that. So that when you are carrying out your experiment, you know when you are making sense and when you are not making sense. If it is traveling from air to glass, that means the angle of refraction needs to do what? Reduce compared to the angle of what? Incidence. But if it is traveling from glass to air, the angle of what? The angle of incidence needs to what? Smaller than the angle of refraction. I hope that aspect is clear. Clear? Okay. Now let's take for instance that we know the angle of incidence. Are you seeing it now? And we want to find the angle of what? Refraction. How do we go about that? It's very simple. We go back to Snell's law again. Snell's law. The Snell's law states that if I have what? The sine of angle of incidence divided by the sine of angle of refraction is equal to the ratio of the refractive index. Is just equal to the refractive index normally. But this is equal to the ratio of the refractive index M2 all over N1. Are you seeing this now? So if I call this one equation star, cross multiplying from here, I will have that the sine of theta 1, sorry, I will have N1 sine theta 1 to equal to N2 sine theta 2. Am I making sense now? So from here, if I'm looking for N1, N1 will become N2 sine theta 2 all over sine theta 1. So I can call this star star. And from here, I can say sine of theta 1 is equal to N2 over N1 sine of theta 2. And theta 1 is arc sine of N2 over N1 sine of theta 2. From there, you can get the value of what? Theta 1. That is the angle of incidence. So I can call this star star star. And if I'm looking for theta 2, or I'm looking for N2, N2 will become what? N1 sine theta 1 divided by sine theta 2. And I can call this star 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 star. I see it now. And if I'm looking for theta 2, I can say my theta 2, or just say that sine of theta 2 is equal to N1 over N2 sine of theta 1. So from here, if you take the arc sine, you have what? Theta 2 to equal to arc sine of N1 over N2 sine of theta 1. And this should be star, 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 star. I hope you get this now. Do we get this right? Sure. So that's how to find unknown using what? The Snell's law. This is just the basic. So you can explore to that particular point there. I hope it's clear. Are we getting tired? Okay. Alright. So if I give you that theta 1 is 60 degree. For example, if I give you that theta 1 is what? 60 degree, you can find theta 2, isn't it? Just plot it into this place. Theta 2 is equal to arc sine of N1 is what? 1 over 1.5 sine of 60. 1.6, Abi? Thank you. Or sine 60. So 1 divided by 1.6 sine 60, what do you have? Or just say sine 60 divided by 1.6. 0.54. So arc sine of 0.54. So what do you have? When you take the arc sine? 32.68 degree. So you can see what the angle look like. Is it bigger than that or smaller? Is it bigger than the incident angle? It's smaller. Why is it smaller? People should talk now. Or are you hungry? Why is it smaller? work now? Because it's moving from what? Air to glass. Are you getting this now? So I've explained all of this, and I think by now you should understand it. You don't just keep on nodding. You're on your own exam. If you keep on nodding from now to tomorrow, it doesn't affect me. So I hope you are cool now. Can we go on? Okay, so let's make this a bit interesting. Let's make it a bit interesting. And how do I want to make it interesting? Can I clean all of this? Alima, you are still doubting something? You sure? Clear? Okay. How about you? You understand? Okay. You're forming levels, no writing. Olopa? Clear? Okay. Alright. So let's move on now. Let's make this look more interesting than what we have here. You know, examiner can determine that in this way, normally, this ray is supposed to travel on a straight line. Are you getting this now? And in fact, I don't just want to take you deep into it, but probably in future, I might be talking more about leftover rays, because this ray that is traveling into this glass is not every of the ray that refracted completely. Am I making sense now? It's two things. Number one, it's not all this ray that entered inside this glass. It's not everything that enters inside this glass. Number two is that it's not all the rays that entered inside the glass that refract. Some still go straight. So that is, some refract rather, while some they still maintain their straight line. Am I making sense now? This one continues straight line, this one refracts. While some they do what? They go back. So what's the interesting thing here? The interesting thing here is that examiner now can at times ask you to find the distance between the ones that refract and the ones that go straight. So I don't think you really need that, but just be aware that it's possible for you to have that. Okay, so for you to, like, a situation that always arises to that is a situation whereby when you have two boundaries. Let me say, okay, let me just use that. Let me go in deeper. How the thickness of your glass affects your result. How what? The thickness of your glass affects your result. Because when you see somebody using a glass that is as thick as this, and when you see somebody using a glass that is as thick as this, they cannot have the same result. Are you getting where I'm coming from now? So the thickness of the glass also affects the refracted ray. So let's see something. Let's say you are given a glass that is thick by 10 centimeters. For example, let me have this and this. So the thickness of this glass is about 10 centimeters. And then you have what? An incident ray whose angle is theta 1. So when you see this now, this is going to refract towards this side because this is air. Refractive index is what? 1. And this is what? Glass. The refractive index is 1.6. Remember, it can be 1.5, depends, but let's say 1.6. And going back to what? Air, whose refractive index is what? 1. Thank you. So from air to glass to what? To air. Now, at this point here, I have another number. Are you getting it now? So it means you're having two boundaries now. So the light travel from air to glass, and then travel from glass to what? To air. So what will happen to the refracted ray? Yeah? Is it going to closer to this what? This, or is going to far away from it? Is it going to move closer to the normal or far from the normal? Far from the normal. Why is it going to be far from the normal? Because from where? From glass to air. It's moving from a denser medium to a less dense medium rather. Okay, so this angle here, there's an angle here, there's an angle here. Are you seeing it now? So let me call this angle here theta 2, theta 3, and then theta 4. Are you seeing it now? And then remember, some of the ray, they are going to do what? Refract when they enter inside this place, while some will continue their journey. So let's say these are rays that continues their journey, and now the examiner now says, what is the distance between these two rays? How far will the refracted ray be from what? The rays that fails to diffract. Well, I say refract rather. So that's what we are looking for. And it's going to be a pleasure if somebody can look for that. Okay. So we are looking for this now. Alright, so let me call out D. I think I learned it to be D. Alright. So this is quite interesting. Absolutely. It's quite interesting if you can give it a time. You see now, the thickness of the glass now is what is bringing about this. Are you getting this now? If the glass is very thin, they are going to have less amount of ray to what? To move straight. Are you getting it now? If the glass is very thick, you have more amount of ray to be what? To be far from each other. Do you understand that now? So let's see how far we can come up with this. And I hope this is helping somebody. Okay. Before anything, we need to find the value of all these angles. But to make our work easier, let me call this one 30 degree. Are you following? So if I have this to be 30 degree, what will be the value of this? I can find this, right? Using what? The Snell law. So theta 2 that we are looking for is going to equal to what? Arc sine. Are you sure of this? Supposed to be what? N1 over N2 sine theta 1, right? Please check. Yes. Alright, so that should be the case now. Follow up, please. Theta 2 is going to be arc sine of N1 is what? What is N1? 1. N2 is what? 1.6 sine 30 degree, right? Okay, so sine 30 degree should give us what? 0.5. So 0.5 divided by 1.6, what do you have? 0.312. Have you? So arc sine of that? I think I've explained this to you several times. It's not called sine inverse. Arc sine. Sine inverse is cosec. Do you understand that now? Sine inverse is cosec. So it's arc sine. Alright? So theta 2 is what? 18.21 degree. Abi? So that means this angle here is 18.2 degree. Abi? Okay, so what will be the value for theta 3? Theta 3 will be what like that? Huh? You see what? The same thing, 18.21, Abi? So why is it the same thing? So I may ask. Because we are still having Z. How do you make the Z? Okay, like this? Huh? Like this? Okay. Alright. I think your Z is working fine. I know the crazy things about learning. You know, the way you decide your own way of understanding it now is better than you trying to force the teacher's own on yourself. You know, the teacher's own selves check for the ones that are parallel, but you always check for the one that is what? Z. So if you look at this line, you see that it is parallel to this line. Can you see? So that's why your Z word actually does what? Work. I don't know why you are getting the Z, so I really cannot tell. Okay, so like this, like this, like this. Abi? Okay, I think probably I'm going to master your Z. So you're absolutely correct. So theta 3 is what? 18.21 degree. Alright, absolutely cool. So we can now find theta 4 now, right? So our theta 4, we can now use Snell's law for that, isn't it? And that will be M2 all over. Sorry. Okay, so the graphs now is going to be like, okay, I think there's a problem right here now. So for better understanding, so that I will not even confuse myself. So I'll call this one now N1. I getting it now? And I'll call this one what? N2. Am I making sense now? Okay. So the refractive index from here now, you know this one is theta 3, right? So that will be 1.6 sine theta 3. I say this now, which is 18.21, Abi, to equal to 1 sine of theta 4, Abi. Am I right, guys? Yeah. Therefore, I have 1.6 sine 18.2 divided by 1 equals sine theta 4. So theta 4 equal what? Arc sine of 1.6 sine 18.2. Are you following, guys? Yes. So what will be our result now? So arc sine of 1.6 sine 18.2. Okay, so I should not stress myself. Yes, so what's the final answer? 29.98. 29.98 degree. Abi? It's dangerous to approximate when you have not arrived at the final answer. Be careful. Are you sure of what you've gotten, right? Okay, so if that is the value for theta 4, then I think we are good to go now. We can find the value for D. Abi? Now, if you want to find the value for D, I want you to observe something here. Look at this. Redrawing is happening now, so pay attention. Look at this. Look at this. And look at this. It is what? A right angle triangle. Agree? Yes. Agree? Yes. So if I call this one, let me call this one P and call this one Q. I see it now. Then Q plus P, let me call it, that is from here to this place, let me call it X. Are you guys following? And from this point here to this place is P. And from here to this place is what? Q. But from here to this place is what? X. So if I can get the value for X, are you getting it now? Then I can try to get the value for what? For Q and the P. Have you? So how do you go now? Because what I really need is the value for P. Are you getting it now? The value for P is what I really need. But it's not going to be easy for me if I don't know the value for Q. And there's no way I can know the value for Q if I don't know the value for what? X. Are you getting it now? Okay, so let's get the value for X now. You know, I can know the value of Q without knowing X. It's possible. But I cannot know what P without knowing what? X. So let's find X first. Now, this is the angle here. This angle here is what? 30 degrees. Do you agree with me? Because vertically opposite what? Angle. I see it now. So that's what? 30 degrees. So if here is 30 degrees, let me draw out the triangle. So if here is 30 degrees, this angle here is what? 30. This height, and listen, this height is what? 10 centimeter. Abi? Yes. And from here to this place is what? X. Abi? Okay. So we can find the value for this place, right? By saying what? 12. Abi? So that is what? The tangent of 30 degree is equal to opposite over adjacent. So x is equal to 10 times 30. 10 times 30 will give us what? 5 point. So 5.774 centimeter. That's the value for x. Abi? So the value for x is 5.774 centimeter. Then we can find the value for q. And now, how can we find that? We still consider this triangle here. I don't have another color marker here. I'm supposed to have red, but I don't, and I'm not sure. So look at this. Just watch. Look at this triangle. Can you see this and this? Can you see? Huh? So if you hate mathematics, you fail physics. No, there's no case. So this will now be palm, palm, palm. Abi? Yes. Here you know what? 10, and this is what? Q. Abi? Yes. And this angle is going to be what? 18.2. Are you saying this now? Yes. Okay. So somebody is feeling herself. 18.2 equal what? Q divided by what? 10, right? So Q equal what? 10 times 18.2. So 10 times 18.2 will give you what, guys? 3.28. So our Q is what? 3.28 centimeter. So if the entire year is 5.774 centimeter, and from here to this place is what? 3.28. So our P is going to be what? 5.774 minus 3.28. So what do you have? 2.494 centimeter. So here is 2.494 centimeter. 2.494 centimeter. Now, okay, I think it's getting interesting now. Now, if I want to get the value for this D, look up. If I want to get the value for this D, if I draw a perpendicular line from here to this place, let me use blue. A perpendicular line from here to this place. Can you see? This is 90 degree, this is 90 degree. Can you see that line? Huh? So this line and this line, they will be the same thing. Am I right or wrong? So this idiot is going to be G. Abi? Okay. So I have here to be D now. Look up. I have here to be what? D. And here is what? 2.494. Abi? So the angle here is what? Theta 4. From here to this place is 90 degrees, isn't it? What is our theta 4? 29.98. Okay, so please subtract that from 90.
60.02.
60.02. So that means this place is 60.02. Can you see that now? 60.02. So let me draw that diagram out so that we can see it clearly. So I have this, this, and this. So this is D. This is angle 90. This is 2.494, right? And the angle here. Okay. There's something else I can do here. Okay. If here is this, right? Okay, this place is what? 60.24, Abi? 60.02. So we can say what? The sine of 60.02 is opposite over hypotenuse, which is 2.494. Abi? So when you cross multiply 2.494 sine of 60.02 will give us D. So what's the answer?
2.16.
2.16. So we have 2.16 centimeter. So that will be our result. Have you seen the distance D now? Huh? Okay. Can you not use ruler and measure it? Yes, you can use ruler to measure it since this experiment. So if you have done the right thing, your ruler can give you the result. Do you get that now? So if you have the time after measuring it with ruler, you can just want to be sure of what you've done. You can now decide to go on by the mathematical stuff, and so long you don't approximate, you can see that we don't approximate throughout. That's why I always tell you that when you press your calculator, don't approximate until you get to the final result, because any approximation on the road, let's say for instance that we have approximated this one to one decimal place now, is going to affect the whole of the result. Your answer will never be 2.16. You can have the answer to be 2.1. You can have this to be 2 exactly. You can have this to be 2.17, but it's not going to be what? 2.16. That approximation has affected. I hope it's clear. Yes, all right. So let's now look at a case of a triangular prism now, which is the main case of this experiment. Okay, I hope you are getting all this clearly. Okay, we are getting closer to the end of the whole thing that you need to know. Okay, so let's say I have a triangle like this, and this is angle 45 degree. I'm supposed to make that angle 60 degree. Yes. Why? Let me make it 60 degree. Do you know why I'm making it 60 degree? I'm making it 60 degree because the triangular prism we are using is an equilateral triangular prism, and the whole of its side is 60 degree anglized. And I just hope I will not cause problem by using 60. Okay, so let's use 60. Let's say this angle is 60 degree. Are you getting this now? And then I have a ray of light coming in like this. So if I have that, this angle here is perpendicular to this surface, this normal. Remember, normal is always perpendicular to the surface. So this is 90 degree. Are you seeing this now? Okay, so let me call this angle here theta 1. So this is the ray that is entering. Okay, so this ray of light travels and strike this. Okay, so when it strike, I have my normal to be this. So if that is my normal, between the normal and this, I have what? Theta 2. Okay, so if that is theta 2, then I'm not getting the diagram right.